Hi there. Over the last few years, I've been talking about what makes good Python code, often by talking about how Python approaches ideas from other programming languages. Now today, I'm here to talk about the Zen of Python, which has been with us since time immemorial. Now we've been using the Zen of Python to help us figure out how to write good Python code. And because many of us are people who get into arguments on the internet, we use the Zen of Python as fuel for those arguments. Now, I think it's a good year to talk about the Zen of Python and its limitations, and to talk about whether it does what we think it does. And I've been a huge fan of the Zen of Python for many years. This was reinforced in a talk at PyCon Australia in 2011, when Richard Jones gave a fantastic deep dive simply titled The Zen of Python. Here's its abstract in its entirety. And it showed how the Zen of Python was used in Python and its standard library. Now, sadly, that talk wasn't recorded, but it shaped how I think about writing Python code, because I saw how to put the Zen of Python into practice. And it taught me ways to recognize whether some code was good Python or bad Python. But in a talk I wrote last year, I looked to the Zen of Python to answer a question. And for the first time, I was left bereft. I had found a design problem in Python, and the Zen of Python couldn't save me. And that's what I've come here to talk about. Tim Peters' 20 Python Theses. No, that spelling is how he introduced it. And yes, there are only 19 of those theses written down, but they've come to be known as the Zen of Python, or PEP 20, or that thing that appears in your terminal when you type import this. And here are those 20 theses. Now, immediately, in that very mailing list thread where Tim introduced it, people thought it was fantastic. They thought it described everything that Python was about. It was concise, it was opinionated, and it explained in very clear terms how Python thought differently to Perl. And in the 1990s, that was super important. Now, in the years following that, people started to identify languages with a prescriptive design philosophy. A good example is Java, which was intended to be familiar to C developers, much like C++, but without all of the ways that C++ would let you shoot yourself in the foot. Now, looking at the Zen of Python, especially its first few lines, also made people think that Python had a prescriptive design philosophy. This was in contrast to, say, Perl. Now, for the longest time, I have referred to the Zen of Python. I've referred to it when introducing speakers at conferences. I've used it to answer questions that have been raised in my talks. And I've used it to solve design problems in my code. I have definitely thought that the Zen of Python was evidence that Python has a descriptive design philosophy. But it's not. Today, I want to show you why the Zen of Python isn't prescriptive, and why it's a terrible way to settle arguments about the right way to do things in Python. Today, we're going to look at two design decisions made since the Zen of Python was written that appear to have ignored the Zen of Python. Then we're going to look at some code that the Zen of Python thinks is reasonable, but isn't, and we're going to look at whether the Zen of Python ruins our understanding of why Python is the way that it is. So, I mentioned earlier that I got confused by the Zen of Python last year. The Python feature that confused me was the decorator. Decorators exist because sometimes in Python you need to modify the behavior of a function or a method. Now, people have been modifying the behavior of functions since well before decorators existed. And one popular way to do this was through a thing called the decorate pattern. The decorate pattern looked like this. First, you define a function, and then you pass that function into another function and you assign it back to the original name. Now, this is fine for short bits of code, but things can fall apart pretty quickly. If you need to decorate the same function twice, well, things get a bit repetitive. And you have to decorate your function from the inside out. So the last decorator applied is actually the outermost behavior at call time. So here, the class method decorator gets called before the synchronized behavior, but you have to define them in the opposite order. And it suffers from really, really poor concept grouping. Decorators can substantially change the behavior of a function, but here it appears after the method body. And if your method is really long, the decorate step might not even appear on the same window as the function declaration. This can make for really unreadable code, and as we know from the Zen of Python, readability counts. So PEP 318 gave us some syntax for the decorate pattern. And now we have decorators. So we know if we read def in some Python code, it means, well, we're defining a function. So if we see a decorator, well, that must mean this function that we're defining has modified behavior. In this case, we know that the new behavior is that it is synchronized and that it's a class method, and it's easy to tell that at a glance. But this won't be surprising if you saw my talk last year. That understanding of what a decorator does isn't exactly true. Because putting a decorator before a function definition doesn't actually change the behavior of the function. It can actually change the definition of a function. Let me show you what I mean. Say you define a function called squares, which multiplies a number by itself. You can then call that function and you get a value and everything is great. Now here's a decorator. This decorator is called apply. When you decorate a function with apply, you also provide a transform lambda, which accepts a function as a parameter. Now when you decorate a function with apply, it will call that transform lambda with the decorated function as its parameter. And instead of returning a callable, it returns the result of that transform lambda. So what if we take our squares function and then we decorate it with apply? And let's pass in map as our transform function. Now, after we define our function, squares isn't a callable, it's a list, because that's what our transform lambda returns. So we just created a function using def to be called once at definition time and then discarded, just because that's what the decorator does. We define a callable, but we end up with a list in its place. The fact that the thing we define is no longer necessarily callable isn't obvious from syntax, but it's there pretty plainly in the old decorate syntax. There's nothing that says this thing has to return a function, and so it is with decorators. And that brings us to the Zen of Python, which says that explicit is better than implicit. And in Python, when you say def name, well, that explicitly means that name is a callable. That's a contract with you, the developer, and decorators let you break that contract easily. So could they have done better? Well, okay, what if we made it so that the things that decorators put in their place are callables? Well, that would solve the immediate ambiguity. But property descriptors, which I think are very Pythonic, are also implemented using decorators. And once you decorate a method with property, you don't call the method you defined by calling it, you call it by accessing or assigning to an attribute on an object. So you're actually calling code as a side effect of something that at a glance has nothing to do with calling code. And you have to know that this property thing does this weird behavior modification. So we see that decorators can turn function definition into implicit behavior that depends entirely on what the decorator function does. So if you follow the Zen of Python, well, you may be asking yourself, are decorators Pythonic? Now, let's skip 13 years of Python evolution and ahead to 2015, which was a much more interesting time in core Python world. Because Python had got popular, and people who'd never got involved in language design before decided to start contributing to design discussions amongst core developers on mailing lists. Now, these people came from a generation of Python developers who'd learned to solve design problems in Python using the Zen of Python, and they understood that simple is better than complex. There's no better demonstration of Python's simplicity than looking at the first program you write in Java. You need to know an awful lot about how to program to write Hello World in Java. You need to know about types, you need to know about classes and function declarations, and Python's version is just so much simpler. But this simplicity has limitations. Python requires you to test behavior with unexpected types. automatically translating code was difficult, which really shot us in the foot in the translation between Python 2 and Python 3. And tools like IDEs, which work really, really well and are indispensable in Java, were complicated to write and unreliable to use as a result. And as the Zen of Python says, well, explicit is better than implicit. And so it was that a feature got added. We used a feature added in Python 3.0 that let us provide argument and return hints to functions. And now you can specify your function's contract with its callers, and these can be automatically tested by a type checker. But in doing so, things become less simple. Providing type hints is an extra piece of complexity that wasn't there previously. And as you add your type hints, your code can get crowded and verbose and a whole bunch of other adjectives that remind people of Java. But type hinting resolves ambiguity that doesn't need to be there. So type hinting laid bare a contradiction. You had to choose between simplicity or explicitness, ambiguity or ugliness. You had to choose where to accept your complexity. The Zen of Python couldn't really resolve this argument. So we see two cases where the Zen of Python just didn't help matters. And if you think the Zen of Python is there to tell you what Pythonic choices are, well, you're probably asking yourself a question right now. Is Python Pythonic? Well, the answer to that one comes from actually reading the Zen of Python. We saw that decorators are a feature that significantly improve the readability of Python code. But in doing so, they take away a feature of Python with quite explicit behavior and they turn it into something implicit. And we saw that adding type hints takes a simple structure and understanding of Python code and makes it more complex. And we saw that not including type hints means that the expected behavior of functions is implicit. These are two cases where the Zen of Python does not guide you towards a good solution. And as Tim Peters said in that original mailing list thread in 1999, if the answer to any Python design issue isn't obvious after reading those, you should give up. If you take the Zen of Python at face value, you'd have to say it's failed to guide Python in the right direction. But I hear you say, these are special cases. They do important things. Well, the Zen of Python says something about special cases as well. It says that special cases aren't special enough to break the rules. But almost as an afterthought, it also says that practicality beats purity. So what does it mean for practicality to beat purity? Well, it means that not everything fits neatly into one of those catchy little boxes the Zen of Python creates for you. It means that sometimes you need to make choices. By the Zen of Python, allowing implicit behavior means that decorators aren't Pythonic, but decorators encoded an existing use case. In the before times, when you want to decorate a function, you needed to sacrifice readability for functionality. And as they were eventually implemented, decorators let you do everything that people were doing beforehand. It meant that every use case where people were decorating functions got covered. And it allowed for innovations like property descriptors. And type hints, well, they solved a real use case that real Python developers could not solve with Python. Inferring the types that a function would accept or return was difficult, and this limited the tools that you could use with older Python code. And if you believe that explicit is better than implicit, well, Python's original approach to typing was not Pythonic, but it did make Python a practical choice for writing programs quickly. The solution isn't simple. Good type systems are inherently complex. Bad type systems make it complex to write code. But they enable simplicity in tests, in tooling, and in automatic translation. So Python chose a system where you could choose to opt out of static typing. There's a rich and useful typing system for people who need it, and if you don't, you can opt out completely. This is the very definition of a practical choice. If you prefer static typing, or if you prefer purely dynamic typing, or if you want a mix of both, you can get the programming language that you want. So Python design decisions value simplicity, explicitness, and a whole bunch of other things, but it also values practicality. And this is a real factor in design decisions, but it acknowledges that not every design problem fits into rules. Or put another way, Python doesn't tell you how to do things. But the Zen of Python also talks about being able to do things. And it says there should be one, and preferably only one, obvious way to do it. And this is an approach that has served the language really well over the years. Basically, it says that you should find a way to do something, keep iterating until it's obvious that it's the way to do things. But that means in order for there to be one obvious way, well, you need to try out a bunch of different other ways first. And quite often, one of the ways that we choose on that path to the obvious way might seem like the one obvious way. I've given talks in the past where multiprocessing and requests were the one obvious way, and they replaced threading and URL open. Well, today, I tell you to use async.io and AIO HTTP. These things became the one obvious way because someone decided that the old way wasn't obvious enough. Finding the obvious way involves experimentation and a certain acceptance that there needs to be a way to do it. And generally speaking, Python is a language that gives you the tools to bend things to your will. Things like Django's ORM are only possible because Python lets you subvert normal behavior and replace it with something completely different. So let's take a feature that Python has deliberately long chosen to not implement, the switch statement. Actually, in this case, we're going to look at its more modern variant, the pattern matching, because, well, Python really should be keeping up with the times. So as an example, we're going to look at one of those terrible programming interview questions, FizzBuzz. Now, to solve FizzBuzz in Python, you usually need a bunch of if and elif statements to solve it. But this version is tedious to write. You need to make sure that you spell the out variable correctly in every one of those if blocks. And you might say, you could refactor this with a function. And I'd say, well, yes, you could, but it doesn't really help. You're still writing return a bunch of times, and you've added an extra line of code, and you've added a level of indirection. What I would prefer is something much more like what Kotlin has to offer. Kotlin's version looks like this. You get to pull the variable assignment out of this when block, and then you're left with just the conditionals and the block of code to execute when that condition is true. It's simple, it's concise, and I really want something like that in Python. And as we know from the Zen of Python, well, there should be one way to do it. And I know the core team has been pursuing pattern matching, but the Zen of Python also says that now is better than never. So what tools do we have right now? Well, if you think about it, these are just blocks of code that get executed under certain circumstances and return a value. And these are the conditions where those blocks get executed. And this is where the value of the executed block of code gets stored. So what we need is a way to group several blocks of code, a way to define the conditions when those blocks execute, and a way to store the output of whichever block executed. So you might ask yourself, does Python have the tools we need to implement this? Well, first up, we have a decorator called case. It's just a boring standard function decorator. It even returns the original function. It just decorates some stuff on the function. There's not really anything magical going on here. Secondly, we have this switch decorator, which is where there is magic happening. It chews up the contents of the class it decorates. It will run all of the functions that you gave to the case decorators as parameters, and will execute the method with the first matcher that passes. Together, the switch and case decorators are written in 37 really sparse lines of Python. It doesn't use anything creepy like inspect or bytecode decompilation, but in combination, they can turn a class with some methods into a functioning pattern matching implementation. And the implementation of FizzBuzz that results isn't terrible. It still suffers from a lot of repetition. If you read the code, it's not obvious why this uses the class and class keyword and methods, but these are the tools that Python has given us. On balance, I think it's less readable than the version with functions that we factored out earlier, but I'd rather inline this than using the multi-if and elif version with variable assignments. Now, this might not be the final obvious way to do it, but it does solve a problem for me right now. And as I can see situations where this could be the obvious way. And as the Zen of Python says, well, now is better than never. Which is to say, well, if you need something, maybe you should implement it with the tools that you have. But it also provides a word of caution. It says that never is often better than right now. And so if we follow the Zen of Python's guidance, we find ourselves in a situation where the only way to do things involves doing something that isn't obvious. And so we shouldn't do that because it's bad Python. But we've seen that Python grows because people try things out and they decide that the best current approach doesn't work, and then they try to improve upon it. So what is practicality here? Is it using the tools that we have to structure code in the way that we want? Or is it making use of what Python gives us and accepting that there may just never be a good way to do something, even if it seems obvious? I've spent the last 10 years thinking of Python in a certain way, and last year I found myself confused by the advice of the rules that we use to write good Python code. And I've been thinking about this fundamental assumption about how Python wants us to do things, this prescriptive design philosophy that I thought the Zen of Python gave us. Or to put it another way, can we follow a set of rules and always end up with good Python code? Over the course of today's talk, we saw that even in fundamental design cases, the Zen of Python, that's PEP 20, gives contradictory advice. Accepting one of the 20 theses often means giving no weight to another of those theses. So it's not a matter of whether following the rules will give us good Python code, it's whether we can even follow the rules at all. PEP 20 doesn't help us be prescriptive, but there is a PEP that's all about being prescriptive. And that's PEP 8. It's a style guide. It tells you exactly what you should do. That is the very definition of a prescriptive PEP. It should be exactly what we want. But if you actually read PEP 8 as far as the first heading, you're confronted with this. A foolish consistency is the hobgoblin of little minds. Now, what does that mean? Well, it doesn't mean that it's bad to be consistent. It actually means quite the opposite. It means that you can be consistent, but you shouldn't be mindlessly consistent. It means that you need to think and to consider whether it makes sense to be consistent in any given case. So the most prescriptive of all the PEPs says that you shouldn't be foolishly consistent. So Python is not prescriptive, but it's easy to think that it is. But it's not that. Python is opinionated. Python is a language that has a strong opinion of how things should be done. And the Zen of Python is just a list of one man's opinions. Mind you, they're generally pretty good opinions, which you can use as guidelines to help you design better software. But at the end of the day, they're just that. They're just opinions. And opinions that you agree with, no matter how much you agree with them, aren't actually rules. No matter how much your favorite part of the Zen of Python guides your development style, it should never be the only factor in deciding what good code is. Remember that different people have different use cases, and Python has grown spectacularly because we support those different use cases. Keeping a narrow view on the use cases that you value doesn't keep Python simple. It just keeps it simple for you. So when problems come up that Python can't solve, keep an open mind that people are actually having these problems. And we can make Python simple for them as well. That should be a guiding principle. So while Python is an opinionated language with a strong design aesthetic, it is that way because the people who've designed Python made choices about how to improve the language. So if you want to write good Python code, sometimes that means valuing some designed opinions more than others. And sometimes both opinions that you have to choose between are in the Zen of Python. So how do you choose? Simple. Practicality beats purity. Thank you for coming along. I hope you've enjoyed this talk. I'm going to be around chatting after this. If all has gone according to plan, I've actually been in the text chat for this talk talking to you. So I will have told you where you can find me after this talk. If you're watching this on delay, you can reach me by email or Twitter. My email address and my Twitter handle are on this slide. And I'll also have notes for this talk, including implementations of everything I wrote up on my website at chrisjrn.com in the blog section. Thanks to everyone at PyTexas for making this event happen. Thank you for inviting me to give this talk. I hope you all enjoyed it, and I hope to see you at a real-life event at some point when all of this is no longer happening. Thank you all for coming along, and see you next time.